In this video, we'll have a look at the exam of January 2022. What we'll do is solve the three first questions. As you can see, there was also a fourth question, but this fourth question was also part of the exam of January 2021. So if you want to have a look at the solution of this question, you'll have to have a look at video 18 about the exam of January 2021. Let us have a look at the first question. Well, you have to find bases and dimensions for all the four fundamental subspaces of the matrix that is shown. And then you have to find the rank of this matrix. As usual, if you're preparing the exam, try to do this exercise by yourself and push the pause button. Let us have a look at the solution of this question. As usual, we start with an augmented system in which we put the original matrix, and just next to it we put an identity matrix. This identity matrix is constructed on the rows of A, so this means that we have here an identity matrix of dimension 4. The reason we do this is that we will quite easily obtain here the vector that would serve as a basis for the left null space, as is shown over here. So what we do is look for the first pivot in the first row, and this first pivot is over here. As usual, we create zeros below the pivot, and this is done by the following row operations, right? If we look at this row operation, this means that we subtract 2 times the first row from the last row, and this will indeed produce a 0 as shown over here. We obtain after calculations the following system, or matrix I should say. We look for the second pivot in the second row, and here it is, right? We have to create zeros below this second pivot as well, and we do this using the following row operations. We then find the third matrix that is shown over here. We can now look for the third pivot in the third row, and here we find indeed a third pivot, and again we produce zeros below this third pivot by the following row operation. And this is what we obtain in the end. Notice that we stop here. Usually what we do is create zeros above the pivots. So we go to the row reduced echelon form. Here we stop and we just obtain the echelon form of the matrix. We do not need to go any further, because here in this case it's easy to obtain the null space. Usually what we do is bring this matrix over here in this format over here. So we have an identity matrix, an F matrix, and then 0 matrices over here. And we do this because this allows us to obtain n. But as you will see here, it's quite easy to obtain n, so you do not need to go to the row reduced echelon form. So we can immediately see that the rank of the matrix is 3, since we have 3 non-zero pivots. So this means that this matrix A here has full column rank. This means that, well, these columns here are independent, so this means that the only x that is such that ax is equal to 0 is x is equal to the origin, right? So the null space is simply the origin over here, right? So we do not need to do this type of computation over here. So let us continue with the column space. We have 3 pivots, so what we can do is take a combination of the columns in the original matrix, right? We cannot take the columns of the reduced form because we have done row operations, and we know that row operations does not preserve the column space. So we take, since there are 3 pivots and we know that the columns are independent, well, we need to take combinations of these 3 columns as is shown over here, right? So we have the column space, we have the null space. Let's have a look at the row space and the left null space. These are associated to, well, A transpose, as you can see. So we look at the rows associated with the pivots. You can do this in the reduced matrix or in the original matrix, since we have done row operations and the row space is indeed preserved. We have here, for instance, 3 rows that are independent, right? So 3 vectors that are independent in R3. If you take linear combinations, what they will produce is actually R3 itself. So in our case here, we have that the row space is simply R3. We can now have a look at the left null space, right? So we see that we produce a row of zeros here. So this means that this vector here can be used to pre-multiply A. So 0, minus 1, minus 1, 1. And this will produce this 0 row vector. And indeed, if you check, this is indeed the case. So minus 1 times 1, minus 1 times 1, plus 1 times 2 produces indeed a 0. And if you continue, you will see that this will indeed produce the following vector here, row vector that is composed solely of zeros, right? So the null space of A transpose can be constructed by linear combinations of this row vector that is transpose, right? And here you find this left null space. Usually what you do is check that the vectors that are basis vectors in the column space, are indeed perpendicular, orthogonal to the base vectors of the null space. So you should check that the, well, scalar product of this one with this one, and this one is indeed 0. And if you do this check, you will see that this is indeed correct. Well, what you can do is look at the first part of the fundamental theorem of linear algebra and look at the dimensions of the different subspaces. We know that the dimension of the row space plus the dimension of the null space is equal to n, is equal to the number of columns, and in this case this is equal to 3. Here the dimension of the row space is 3, the dimension of the null space is 0, so this is indeed correct, right? We know also that the dimension of the column space plus the dimension of the left null space is equal to m, which is equal to the number of rows, and here this is equal to 4. Dimension of the column space is equal to 3, and the dimension of the left null space is equal to 1, so indeed this is also correct, right? And the dimension of the column space and the dimension of the row space are equal to r, which is equal to the rank of A, and as you can see, this is correct as well. So this concludes this first exercise, this first question of the exam. Let us have a look at the second question. Here we have to find the values of k for which the system of equations ax is equal to b, with a and b shown, has no solutions, an infinite number of solutions, and a unique solution. And then for the values of k for which there are an infinite number of solutions, you have to express this solution in full detail. As usual, try to do this exercise by yourself if you're preparing the exam. So push the pause button. Well, let's have a look at the solution of this second question. As usual, what we do is create an augmented system. So you recognize the A matrix over here and here the B matrix, and we'll do pivoting on this system over here. So let us look at the first row and try to find a pivot. Easy to find over here. We have the pivot 1. It's independent from K, so there's no discussion over here. It's 1, it's different from 0, and you can use it to create zeros below the pivot as shown over here, and therefore you have to use the following elementary operations. After computation, this is what you obtain, okay? And now you have to look for a second pivot in the second line. So if you have a look, well, you find that this can be a pivot, but only if this pivot, of course, is different from 0, right? So this presupposes that K is different from 1. If it is not, if it's equal to 1, well, you'll have to treat this case corresponding to K is equal to 1 separately. This is what we'll do over here. But here we'll assume K is different from 1, so this pivot is different from 0, so we can use it to create zeros below the pivot, and you can do this using this simple elementary operation. If you do this, this is what you obtain. Well, now we have to start the discussion, right? And what we'll do first is consider this case. K is equal to 1 that we have missed. Of course, this is only valid here when K is different from 1. So what we'll do is come back to this situation and plug in K is equal to 1, and this is what you obtain. You can quite easily see that the last two equations are incompatible. This one says that the last element is 2, and this one says that it's 5/3, right? In this situation we have no solutions because the two last equations are incompatible. If you now look at this situation that is valid when K is different from 1, you can see here that you have, at least when K is different from 0, an upper triangle matrix, and therefore you'll have a unique solution because you can find the solution by back substitution, right? So the only case that we have to consider now is the case where K is equal to 0, because this generates here a line of 0. So we know that we'll have an infinite number of solutions, right? And here the question says, in this case, well, you have to express the solution in full. Well, let us come back to this situation over here and plug in K is equal to 0. If you do this, this is what you will obtain. And as you can see, well, the situation is quite easy because we recognize over here the row reduced echelon form. We have an identity matrix, we have a F matrix over here, and we have the 0 matrices over here, right? So we can construct the overall solution in this case by taking a particular solution plus a linear combination of, well, the basis vector from the null space, right? So how can we find this particular solution? We take this vector here that in the course is called dp, and we put a 0 below. By construction, it's a particular solution of the original system, ax is equal to b. I'm not going to do it, but what you should do is check that it is indeed the case, right? So what you have to do is consider a and b when k is equal to 0, and then check if a times xp is equal to b, right? And then we have to add a linear combination of the basis vector coming from the null space. Well, this basis vector of the null space, we have seen in the course that it's, well, minus f here with an identity matrix below, and here this identity matrix is simply the scalar 1. And again, you should check that a when k is equal to 0, right, times xn is equal to the 0 vector. If you do, you will see that this is indeed correct. So here we have the three cases. K is equal to 1, no solutions. K different from 0 and different from 1, of course, unique solution, so we better add that here. Unique solution, and when k is equal to 0, we have an infinite number of solutions, and we have expressed the solution in full detail. This concludes the second exercise, the second question. Well, let's have a look at the third question, which is a bit longer to read, and you have to take your time to understand the question. So you have an unknown signal x of k, right? So x of k, and it is unknown, and it's that signal that you'll have to estimate, right? That goes through a channel, a communication channel, right? And it's modeled by its impulse response. And at the output of that channel, well, you measure yk. So that's a known thing because it's measured, and the channel is known as well. And the idea is to, of course, estimate this one, right? Well, you know that xk has a support n, which means that for k larger or equal to n, xk is equal to 0, right? So support is equal to n, right? And your channel has also a finite support, which means that hk is 0 for k larger or equal to m, right? So support is equal to m, right? And by the course of signals and systems, you know that the support of this one here will be simply the sum minus 1. So m plus n minus 1, right? And you know that, well, yk can be written from the convolution sum that is given over here, and that comes also from the course of signals and system, right? And the question is, can you write this estimation problem? You remember that you have to estimate the signal x of k that is unknown, that has been emitted, knowing the channel and knowing the output signal that was measured, right? This is called deconvolution, right? Can you write this as a least squares problem, right? And then we take a particular example where you have here the impulse response of your channel. M is equal to 2, that's the m over here. So we only have, well, a finite impulse response with two elements that are different from 0. They are given over here, and well, we know that the signal that has been emitted has finite support, n is equal to 2, so only x0 and x1 are different from 0 and have to be estimated, right? And then we have measured at the output of the channel a signal y of k, right? And of course it has support m plus n minus 1, in this case 3. So this explains why we only have 3 elements of the response that are non-zero. And the question is here, since you have written this problem in a least squares problem, can you, for this, well, particular case here, estimate x0 and x1? Let us have a look at the solution of this exercise. let's first go back to this convolution sum. We have sum up to k here, because when m is larger than k, this argument is smaller than 0, and since xk is causal, well, xk is equal to 0 for k smaller than 0, right? For negative arguments here, this is a 0 and this does not produce any contribution, so this is why we see the k over here. Similarly, we have m is equal to 0 over here because the system is causal, its impulse response is causal, so hm here is 0 for m that is negative, right? So in order to write this as a least squares problem, we have to write y0 up to ym plus n minus 2, right? So here is the measurement vector. The first element is y0, the last element is ym plus n minus 2. So there are m plus n minus 1 rows in here. So we can write this equation here for k is equal to 0, k is equal to 1, etc. If you write it for k is equal to 0, you'll have only one term in the sum. You sum from 0 to 0, so you'll have h0, x0. If you have k is equal to 1, you'll have two elements in the sum. You'll have h0, m is equal to 0, x1, because k is equal to 1, m is equal to 0, plus then m is equal to 1, and then k is equal to 1, m is equal to 1, x0. And you can continue to write the output for y up to ym plus n minus 2. Here you have what happens for y2. You have, of course, a number of unknowns here, and the inputs here are the unknowns. We know that xk has support n, so we will have n elements in the vector x from x0 to xn minus 1, right? So these type of equations, if you stack them, we can write it as a system of equations. hx is equal to y, where h is constructed as follows. At some stage here, because h has a certain support m, there will be an h here that will be 0, right? But this is how you construct the least squares problem. So let us look at our example here. We have here m is equal to 2, right? So this means that our channel has only two elements in the impulse response, the others are 2. N is equal to 2, so the signal we're emitting and that we want to estimate as only two non-zero x's, right? And this means that we'll have m plus n minus 1, so 3 measurements. The first one, y0 is 1, y1 is equal to 3, and y2 is equal to 2, right? So we'll have here, in general, we have m plus n minus 1 rows. So in this case, we'll have 3 rows, right? And we'll have 2 columns since n is equal to 2. So here we'll have h0, 0, h1, h0. Here we'll have h2, right? But h2 is 0 and h1, right? So if we plug h0 and h1 in the matrix, this is the h matrix that we have. Here is our vector of unknowns. It consists only of x0 and x1, since x has support 2, and here is our measurement vector. So in our particular case here, our least squares problem is as follows. Well, let us have a look at our solution to the problem that we have defined, and the solution of this problem over here. Well, you can see that you have a system of equations, and in this particular case, well, there is an exact solution, because this vector here can be written as a linear combination of these two vectors, you can see it, the combination is 2 and 1. So it's not really here a least squares problem. But this is because we have measured y exactly. In practice, what you'll have here is, well, something plus noise, right? And instead of 1, you'll have maybe 1.1. Instead of 3, you'll have 2.95, etc. So this system of equation will not have an exact solution, so you'll have to find a solution in the least squares sense, right? So the idea is to solve this problem in the most efficient way. We make the assumption that, well, you'll have to solve this problem again with the same channel. So this means that the h here will remain the same, but with other measurements, right? So this means that y is changing because, well, you're emitting a different signal with, again, n is equal to 2. If you have to solve it again, then the best way is to solve this least squares problem using a QR decomposition, right? So if you decompose h in QR, you can rewrite the problem as follows. If you multiply on both sides by q transpose, since q is orthogonal, you have the identity matrix over here. So you end up with this system of equations, and it's very easy to solve, right? Because R is upper triangular. So let us take the QR decomposition of this matrix. I've called it A here, but it's really H, right? So what you do is you keep the first column, right? And then you give it a unit length, and this is how you obtain Q1, right? And to obtain Q2, what you do is you construct a vector that is A2, where you have subtracted the projection of A1 on A2, right? So this is A2, and this is the projection of A1 on A2. If you compute this one here, well, it's 1. It's scalar product of this one and this one over here. So that's 1. And this one here is, well, the scalar product of A1 bar here by itself. So it's the length of this one squared, right? So that's a 2 over here. So A2, here it is, minus a half A1 bar, and this is how you obtain A2 bar, right? In order to have a vector with unit length, it's easier to work with A2 tilde. It's really this one multiplied by 2, right? Now it's much easier to give this vector here a unit length. You can see here that if you take the scalar product of this one by itself, you have 6, so you have to divide by the square root of 6 to give it a unit length, and this is how you obtain Q2, right? You have Q1, Q2. This means that you can construct the matrix Q, which is orthogonal by construction. You're looking for an R such that A is equal to QR. You multiply on both sides by Q transpose, and this will yield R is Q transpose A. So here you have Q transpose, here you have A. If you multiply, this is what you obtain, and this matrix is indeed upper triangular. In order to solve the problem, we still have to compute Q transpose Y, with Y the measurement vector. So here you have Q transpose, here you have Y, and here we have Q transpose Y. We can now write this system of equations, and you'll see it like so, right? So indeed this matrix is upper triangular, so this means that you can work using back substitution. The second equation is easy to solve, right? This yields x1 is equal to 2, and if you inject x1 in the first equation, you can easily obtain x0, which is 1 over here. And this is the solution of our least squares problem, right? And you can easily now obtain the solution for another problem with another x and another y, all you have to do is recompute q transpose y. You change this column over here, and again you'll have a system in upper triangular form, which allows you to obtain the solution very quickly.